or base of 50. All right, so it's okay. Last thing I want to show you, we have equations that should go with those points, right?
Yes.
So let's try to graph our equation at this point. How am I going to graph that equation? How am I going to graph my equation?
Oh, that's a good question.
Either one, it doesn't matter, just one of them. So I first need to hit menu. Let's agree there.
Another menu.
Well, yeah, I need to graph my equation. Where am I going to go? Graph entry / edit, number 3.
This game.
And I'm going to graph a,
My eyes are blinking.
No.
Wait, no, it's scatterplot.
well, we already did the scatter plot.
Oh,
I'm trying to graph
what's the
the
P word?
Here.
Patagram?
parabola?
No, what? The P word. Oh, a bunch of P words. Parametric.
Oh, that P word. No. These are called functions.
That's what I said.
They're functions. So we're going to graph a function, type either of those equations in. I'm going to check in on Maddox, but type in either of those equations,
It's not
see what happens.
Straight on.
Remember those explicit equations we created? Yeah, the area equals. Type in either of those. Hey guys, don't put A in. It's just, because f of x is the output. You're just typing in what's on the right-hand side of the equal sign. Notice we already have the output equals. You just need the right-hand side of the equal sign. So you could do, well, oh, by the way, you also need to use x, because x is the input. So you need 50x minus x squared.
That's why I wasn't working.
That's, yeah, if you have b's in there, you need to fix that to x's. That's my bad.
You told us the copy.
I know. B is better in terms of context.
These.
So what is
What
does that equation do?
50x.
It makes a.
This is so cool.
Be careful, it doesn't draw a line, it draws a curve. Specifically, what type of curve? Concave down, parabola. Okay, EK, looks like you have a question.
Oh, no.
Okay.
It's maximum. Right?
Sorry, that's our normal. No, we got more time. Okay.
What is
Wait, what can we get out of that?
Later because of the ACT testing.
Oh, I was up there.
Okay. Say again.
You can do either.
Because you put in B instead of X. Hit escape. Alright guys, make sure you put in X, otherwise it won't work. But notice we have that 50x minus x squared. You also could have done the x times 50 minus x. Oh. By the way, okay, this is something goofy that I hate about this calculator. If you notice, when I hit enter it says invalid input. That's because I didn't put a multiplication sign between the x and the parentheses.
But that's understood there.
We understand it, the calculator does not. I want you to notice, you see how both of these equations and what's called as map right on top of each other? Because they map right on top of each other, that's how we know that these equations are not equal, equivalent. They look different, but are they different? No, they're still the same. So the idea of equivalence is that they may look different, but they're still the same. And so, again, there's our graph for a parabola. For quadratics. Thanks, I do what I can. I've taught this a lot more as well. By the way, there's one thing we still have not covered from our objectives. Anyone know what it is?
Oh,
The Venn diagram.
Venn diagram.
We still need the Venn diagram. That's from the agenda, from the objectives. What defines a quadratic function?
Evidence.
What defined a linear function?
Constant additive rate.
Constant additive rate of change. What defined the exponential function?
Multiplicative.
Constant multiplicative rate of change. So the rate of change. What's the rate of change for a quadratic?
A constant.
Dividive.
You're just randomly guessing, right?
No, it's a
What? Where did we look to find the rate of change? Guys, we haven't talked about this yet. Listen, where did we look to find the rate of change for linear and exponentials?
Slope.
That slope's only for linear. Where did we find the rate of change?
in the algebra.
It wasn't in the algebraic.
Table.
Didn't we find the additive rate of change and the multiplicative rate of change in the table first?
Yes.
Okay, so we need to go back to our table. Alright. Just look at the outputs, don't look at the inputs. Within your small groups, take a couple of minutes to see if you can find any pattern to these, and that's our last thing that we're going to learn about today. So, well, I'll have you do the Venn diagram in your small groups too, but find that pattern. What is happening to that area? So talk with each other, see if you can find a pattern in that area right there. I will say it'll help you if you write down the table, because then you'll be able to write to identify that pattern.
Look, it's like you go. Yeah, it's like P's right there, and then go back.
I'm a good teacher.
Anyone found a pattern yet? Let me say this. If you write it down, you might start to see the pattern. Hey, what's the pattern y'all found? But remember with the linear and exponential, how we identified very clear, like it was adding by this much or it was multiplying by this much. Guys, with your pattern, you should be able to identify what it's either adding by, subtracting by, multiplying by, something like that. So write it down. You won't see it at first, but I promise you, if you write it down, you'll start to see the pattern. I would write that table down and then start to look, and you will be able to find it. Stop bouncing back and forth. Write it down. You're supposed to be looking at that area to figure out what the pattern is. Just focus. So you got enough right now, Max. Just look at the area. What is the pattern? What's it changing by? Yes, Tristan. So, well, now be careful. I want you to know that it is added. Actually, it technically went from 0 to 225, so it added 225, then it added 175, then it added 125, then it added 75, added 25.
It's my well, I mean, it is.
Added 25, then actually subtracted 25. Right? You go from 625 to 600. And then you go from 600 to 525, it subtracted 75. So this is the rate of change right here. And so what you're saying is that the rate of change is also changing. We'll come back to that in a second. Identify exactly what it's changing by.
That's like not a pattern.
Did you find anything?
Back and forth, that's what it is.
Yeah.
Back and forth to 175.
Y'all should be talking about it this whole time.
That's what it's like.
Active collaboration matters, y'all.
I don't understand. Like, I thought it was 175 to 125, but then you're right there and it's negative.
It goes one to like go down. It goes
I thought it was like 175 to 125.
Thank you. Thank you. Thank you. Okay? So some of us have started to find it. And you didn't have to make it complicated. You had to just, do what we did before. So I know at least Cole found it. I know group 3, which I want to emphasize, group 3 found it together, right? Active collaboration is what I'm looking for. I would much rather see a whole group struggle and not get it than just one person at a group get it. Actively collaborate and talk. So group 3, tell us, what did y'all look at? So I've got my table here. What did y'all see? The rate of change is changing. Can you tell me a little bit more about the rate of change? Start at the very beginning. What did y'all do at first? Okay, so tell me, What was it?
Oh, it was plus 225 plus 175.
Oh my gosh, that's what I said. You looked at it.
Plus 25 minus 25 minus
Ooh, hold on. I'm almost there.
Oh, you can get out of there.
Say that again, someone in the back.
Change by 50.
Oh, so there's a pattern.
She said
I want y'all to notice, because y'all laughed when Tristan said this at first. He said the rate of change is changing. That's my rate of change right there. Is it changing?
It is.
It
ain't changing though.
And it's not just changing, it has a pattern to it. How much is this changing by? So minus 50 here. This is minus 50. Minus 50.
Okay.
So I'm going to pause for a second. I want to re-emphasize this. What is math?
Oh my
God, study of patterns and relationships. Okay, so it's there. You don't have to get wild about it like Clay is, but it is kind of cool that it's there. So I want you to note something. I need you to pay attention to this. We have already studied one function that has a constant additive rate of change. Now I need you to hear me very clearly on this. This right here is constant additive. That is not the rate of change. This orange section, not purple, this orange section is the rate of change. But what type of function had a constant additive rate of change? A linear what? Function. Okay? This is not a function, but this is a rate of change. What type of rate of change is that purple section?
Constant.
Oh, this was constant. So this rate of change is linear. And what did you say? Linear additive. So a linear additive rate of change. This is foundational to a lot of what you can study with mathematics. You will go deeper into this idea if you ever take a calculus class. But one of the most fundamental things we want to recognize here is that a quadratic function has a linear additive rate of change. That is a detail that unfortunately most math teachers aren't aware of or don't pay attention to, because we're so not used to thinking about patterns and relationships. So many math teachers are used to you just memorizing content, but that's not useful, nor is it fun. This is a beautiful pattern that we can find here. Everything within mathematics has patterns built in. And that's what we want to discover in this class. Trust me, do what I ask you to do. Look for that rate of change. So, this is it. These are all the foundations for quadratics. This isn't all we're going to learn about quadratics, but we want to be aware, well, hold on one second. We want to be aware, what's the shape of the graph for a quadratic?
Concave down.
Well, this one's concave down, but it is starts with a P, parabola. The shape of a quadratic graph is a parabola. It can either be concave down or concave up. The equation, there's multiple equations, factored form, there's standard form, there's another one called vertex form, because what's this maximum also called?
Vertex.
A vertex, right? So we're going to have a vertex form. And then when we look at that table, we can see what about this function. When we look at the table, what do we find?
Patterns,
It's not constant additive.
rate of change.
The rate of change, which is linear additive, right? There we go. So we want to be aware of these things. These are the foundations. You need to have all of these things in our notes so that we can go back and study them later. I will leave these things on the board. Now, at this point, the end of class, I'm not going to teach you anymore, but your job is to fill in this Venn diagram. Whatever you don't get done in class tonight, or in class, is homework and it's due tomorrow. So what we're going to do is fill in the different sections of this, right? So there's this part in the center that is an overlap of all three types of functions. Does anyone know anything that would be the same for all three functions? They all have, we wouldn't call it a formula, but they all have equations called, what type of representation? Algebraic representations. All three of them have, what else? They all have tabular representations. They all have graphical representations. So we want to note that. They also all have a rate of change, don't they? Right? So all have graphical, algebraic, and tabular representations, right? And so those are things that you could write about here, and rate of change. But then you want to look to see, hey, where do they overlap in each of these sections? Because, well, how do exponential and linear functions overlap? They both have what type of rate of change? Constant. One's constant additive, one's constant multiplicative, but they both have constant rates of change, don't they? So you need to look through your notes. You can collaborate with each other to fill in these different sections, identifying what is unique to each one, what do they overlap in, and things like that. Yes? Yes. All right. They all have graphical, algebraic, and tabular representations.
I've already been noted. You can't use
I had one of them, I might have to print one out. There we go. Maybe I had one more. All right. Here you go. Yep. No, because remember, a quadratic doesn't have a constant rate of change. Quadratic, remember, had that linear additive rate of change. Remember how the rate of change for a quadratic changed? This is the rate of change. The first set is always the rate of change. So, quadratic had linear additive. Does that make sense? So that's something that you could look at here. Where do linear and quadratic overlap? Well, they both have additive rates of change. Does that make sense? So those are things you would want to consider.
Tabular, but yeah.
But no, because that one had to just change.
It's just linear.
Without
Oh, wait. This, no, this is not.
You said quadratic and linear, both additive?
Oh, we're about to actually wrap up. Sorry, I didn't realize how late we went. So, finish up the Venn diagram for homework. I will collect it, make scans of it to make sure that you at least attempted it before class tomorrow. So just do as much as you can, but apparently the bell's going to bring you just a couple minutes. Use like Adobe Scanner and take a video. Just email me a picture of it, okay? And the video will be up on YouTube sometime tomorrow. Okay.
How do I roll out?